In our next section, we're going to talk about analyzing graphs, where we look at graphs of functions and use our derivatives to actually get pictures of those graphs. But before we can do that, we need to talk a little bit about asymptotes. And asymptotes you probably remember from your pre-calc class. We had different types of asymptotes. Mostly in the pre-calc class, we looked at vertical and horizontal asymptotes, but we're going to look at a third case here as well. In addition to the different types of asymptotes, we're also going to look at how to find them using limits. Okay? So let's start with the vertical asymptotes. As you remember from your pre-calc class, vertical asymptotes are any place our function is basically undefined. In terms of the limit, the line x equals a is considered a vertical asymptote if and only if the limit as x goes to a from the right is positive or negative infinity, or the limit from the left of a is positive or negative infinity. One of those two conditions must hold in order for x equal a to be a vertical asymptote. In terms of the pictures, we've got a couple different pictures we can look at. So if this is my point A, I could have coming in from the right and the left, it's going to the same thing, where it's going to positive infinity, or likewise, coming in, they're both going to negative infinity. But it's also the case that it doesn't matter that both of them go to the same, it's this big or here. So I could have one side going to positive infinity and the other side going to negative infinity, and I still have a vertical asymptote there. More importantly, I don't need both sides to exist. So the left-hand limit could exist and the right doesn't necessarily need to have a vertical asymptote. Okay, so one last picture would be, again, if this is my point A, I could just have it coming in from this side and the other side is not defined, and I still have a vertical asymptote. Okay. For horizontal asymptotes, again, these are ones we kind of looked at in pre-calc. Dealing with the function y equals 1 over x, we had both a vertical and a horizontal asymptote. Here, y equals b, so again, notice the difference between x equals a and y equals b. X equals a is a vertical line, y equals b is a horizontal line. So this is a horizontal asymptote if and only if the limit as x goes to positive infinity or the limit as x goes to negative infinity goes to that value b. And again, we have kind of the same pictures, just going the other direction. Okay? So if this is my value b here, I could have where it's coming upwards and going to positive infinity, where the x's are going to positive infinity and the y's approach b. I could have it where my x's are going to negative infinity and it's approaching b. And both of these could be reflected. So it doesn't necessarily have to increase to b, it could also decrease to b. So again, if there's my b, I could have it coming this way or this way. Okay. And you may have some functions where both of these occur. So maybe as it goes to positive infinity, it approaches this value b, and then over here, maybe it approaches b that way. Okay? It doesn't have to be one side or the other, but as long as one of those limits approaches some value, so an actual numerical value, then I have a horizontal asymptote. This last case is a little trickier. So if I look at an oblique asymptote, this is one in which I'm now looking at a curve. It does not necessarily have to be a line, but the curve g of x is an oblique asymptote if and only if I look at the limit between f and g as x goes to infinity, if that limit comes out to be 0, or the limit as I go to negative infinity between f and g goes to 0, then I have an oblique asymptote at g of x. Okay? And basically all this is saying is kind of two pictures that come to mind. Let's say there's my g of x, and my curve as it goes to positive or negative infinity does that kind of thing. So as I move further away from the origin, my values get closer and closer to that line. Okay? Likewise, I could have something where it's not linear. So let's say that's my g of x, and my function follows the curve this way. Okay? So again, as I move further away from the origin, my values are getting closer and closer to the parabola. Okay? So those are some examples of what we mean by vertical, horizontal, and oblique asymptotes. So let's look at a couple of examples. In this first example, f of x equals x squared minus 4x over x squared minus 4x plus 3. We want to find the asymptotes for this function. Okay. Our vertical asymptotes, like we said, are usually the easiest to find because we're just looking for where the function is undefined. So here, if I look, I can rewrite this function as x squared minus 4x over x minus 3, x minus 1. Okay? And so here it's very easy to see. If I look at the limit as x goes to 3 from the positive side, or the limit as x goes to 3 from the negative side, because I get 0 in the denominator, these are going to go to plus or minus infinity. Okay. In this case, I don't actually care which one it goes to. I just care that it goes to something infinite. Okay? And because it's going to something infinite, this tells me that x equal 3 is a vertical asymptote. Likewise, the same thing can be said about x equals 1. If we look at the limit as x goes to 1 from the negative side or from the positive side, we can see that these again are going to be infinite limits. Okay, so we again get that x equals 1 as a vertical asymptote. As far as horizontal asymptotes go, again, the idea is if I look at an infinite limit, what does the function value go to? Okay. So here, let's look at the limit as x goes to infinity of x squared minus 4x over x squared minus 4x plus 3. Okay. Well, again, it's an infinite limit for a rational function. So the first thing to think about is what happens to those dominating terms. Okay, so if I look at the dominating terms here, that's just x squared over x squared, which is the limit as x goes to infinity of 1, which is just 1. So y equal to 1 is a horizontal asymptote. And you can see that if I look at the limit as x goes to negative infinity, I'm going to get the same thing. Okay. Let's look at this next example. Okay, so for this one we have f of x equals 2x squared over x squared plus x minus 6. Okay. So again, first thing I'm going to do is rewrite my function. So we've got a 2x squared over an x plus 3, x minus 2. By the same argument as in the last example, we can see that x plus 3 and x minus 2, if I take the limits as x goes to either of those from the positive or the negative side, again, we can see that they're going to go to positive or negative infinity. And again, just for more clarification, what we mean by that is if I'm looking at these functions coming from the right or the left to those particular values, the bottom is going to 0 and the top is going to something not 0. That's what's making it go to something infinite. Okay? And again, I don't care if it's positive infinity or negative infinity. The fact that it goes to one or the other tells me I have vertical asymptotes at x equal negative 3 and 2. Okay. Let's look at our horizontal asymptote. So let's look at the limit as x goes to infinity for this function. Okay. Now here notice if I look at my dominant terms, this one doesn't quite go to 1. My dominant terms here are the 2x squared and the x squared. So when I simplify, the x squareds cancel out and I'm just left with 2. So this tells me y equals 2 is the horizontal asymptote. Let's look at one last example. F of x equals 10x squared plus 9x plus 5. Okay. So again, for the vertical asymptote, this one, notice I don't have to factor much. I can actually just look at this and see that the limit as x goes to negative 2/5, positive or negative side, both of these are going to put a 0 in the denominator and something non-zero in the numerator. So this tells me that limit is going to go to infinity, some infinity. And so our vertical asymptote is x equals negative 2/5. Okay. In this case, if we look at the limit as x goes to infinity, we can see that the dominant terms here are the 10x squared and the 5x. But when I simplify, notice here my limit is now being taken of a 2x. And if I'm taking an infinite limit of that, that's going to go to infinity. Okay? So this tells me I don't have a horizontal asymptote because that infinite limit didn't go to a number. But this tells me that I do have an oblique asymptote. And so the only way to find out what that oblique asymptote is to figure out what my g of x is that's going to make that 0 when I take that infinite limit. Okay? Now that seems hard to do, but the way to do this is to use some division. Okay? If you remember your long division and synthetic division, you can use either one. So now that I know there's no horizontal asymptote, let's look at oblique. Now again, for an oblique, I need an f minus g that the limit goes to 0 as x goes to infinity. Now to find that, that's not always easy to do. And so one of the first things I want to consider is rewriting that function. And the easiest way to rewrite that is to divide out. So I'm going to use long division to rewrite. I basically want to find the quotient and remainder so I can rewrite this function. So I'm going to multiply by 2x to get a 10x squared plus 4x. We can subtract that to get 5x plus 5. Then we can multiply by 1 to get a 5x plus 2. Subtracting gives us a remainder of 3. So this tells us our f of x is going to be 2x plus 1 plus 3 over 5x plus 2. So there's our quotient and our remainder, which means our g of x we want to be 2x plus 1. So here, when I take my f minus g, the limit as x goes to infinity, we can see the 2x plus 1's will cancel, and we're looking at the limit as x goes to infinity of 3 over 5x plus 2. And at that point you can see that our limit as x goes to infinity is just going to be 0. Okay? Again, there's my f, there's my g, so this is going to be my oblique asymptote. Okay. Now, this process is basically a long way of saying, if I have a rational expression and the limit as x goes to infinity is infinite, if I divide out, then the quotient is going to be my oblique asymptote. Okay? That's a long process to do it. If you can do your division and find your quotient, that is always going to be your oblique asymptote.